So next point is rotational energy levels. Now consider a diatomic molecule like HCl. Okay. So this molecule we know have masses m1, m2. Now we know it can rotate. Okay, so rotate. It will rotate about its axis of rotation, going through its center of mass. Okay, here center of mass O. Now this distance we can take it as R, complete distance, and this distance of first molecule will be R1 and the second one R2. Now we know this rotating body has moment of inertia I and it is rotating with angular velocity. We know this molecule can rotate. Now as it rotates, it will create or it will generate the rotational energy value, energy states or energy levels. Okay, so we need to find out expression for that energy level. So from the definition of center of mass, we know m1 r1 is equal to m2 r2. Okay, so we know this relation. Okay, this is center of mass, this is mass m1, mass m2, having the distance r1, r2. Okay, this is complete R internuclear distance. So this is diatomic molecule. Consider the diatomic molecule like HCl. Okay, HCl, O2, H2, N2. So molecules like this. Now here we know this R and written as summation of R1 plus R2. Okay, from this equation we know R1 is equal to R minus R2. So putting this value of R1 in this equation, we get M1 R minus R2 is equal to M2 R. Now from this equation, we can get the value of R1 as M2 R by M1 plus M2. Then similarly, value of R2 is M1 R by M1 plus M2. So these two will be the values of R1 and R2. Now we know the moment of inertia. The moment of inertia I M1 R1 square plus M2 R2 square. Okay. Now we have the values of R1 and R2. So we can put the values here for this I. Now, okay, let's put this value on this value of R1 here, M2 R by M1 plus M2 whole square plus M2 value of R2 M1 R by M1 plus M2. We are finding the expression for energy. Okay, energy of each rotational energy level. Okay, so here solve this. Moment of inertia will be M1 M2 square R square by M1 plus M2 whole square plus M2 M1 square M1 plus M2 whole square. Now we can see this equation and can take out the commons here. So we know here it will be M1, M2 common in both terms, then this denominator M1 plus M2 whole square, this R square also is there. So we can take out these commons outside. We are just taking R out. Okay. We need to show some terms later. So we are just putting that R inside only. Here, what is left? M2 R by M1 plus M2 by plus M1 R by M1 plus M2. So in this step, we have just taken out the commons from this last step. here M1 and R is common in the both terms we can see, and the M1 plus M2, one bracket is outside, another one is inside. Okay, so here we know this is R1, this is R2. So putting these two values M1 and by M1 plus M2 into R, and this one is R1 plus R2. So R1 plus R2 is nothing but R. So we will write for this mu and R square. So moment of inertia is nothing but mu R square. Here mu is reduced mass, this bracket. This is nothing but mu, which is called reduced mass of this two body system. Now here we can see I is equal to mu R square. Now here it's only R, single distance, and mu, that is reduced mass, single mass. So we just reduced this two body problem into single body problem. Okay, so this is moment of inertia for a single body. Now here, if the molecule starts rotating with angular velocity omega, then that system will have this angular moment. Okay, so moment of inertia, angular velocity. So this will be the angular moment. Now we know angular velocity is L by I. Here, if the system is rotating, it will have a kinetic energy E. Okay, the kinetic energy E, which is half of I omega square. We know this. Okay, so just putting the value of omega here, L square by I square. Then this side gets cancelled. So the energy is E half L square by I. We know the value of I mu R square. Okay, so that will be energy. Now this statement shows rotational energy level of a diatomic molecule. Now here we know this is a variable, so we can take all the values, all the possible values for this L. So we can get all the possible values for energy values, okay, or energy levels. Now, so this will be continuous energy levels, okay, according to classical mechanics, because L can have any value, okay. So L can have any value, E can have any values. So all the possible values are possible. Hence, the spectrum or the spectra is continuous in classical mechanics, but in quantum mechanics it is not continuous, it is discrete one. Now here we have the formula for angular momentum under root j plus 1 h by 2 pi. Here j is nothing but rotational quantum number. Okay, the value of this L into this E. Okay, so this L goes here. We will get this equation j plus 1 8 pi square mu r square dot h square, where mu r is I. So this will be the resultant energy values for each j, where j has the values, j is quantum number 0, 1, 2, 3 and so on. So j is a rotational quantum number, sorry, yes, it is a rotational quantum number, so it can have these values. So from this one, we will get each energy level for each value. Okay, so like this, we will get all the energy levels and their value for each energy level, each rotational energy level. So this equation gives all discrete values for each rotational energy. Here, next point, rotational spectra. Now we know this expression is for rotational energy levels. Okay, so we just put the value of rotational quantum number j, and we will get that energy value for that particular rotational energy level. Now here we are writing it in terms of BCH, where h is Planck's constant, c is speed of light, and b is rotational constant here. Okay, so b is nothing but rotational constant. Okay, so we are just writing it in terms of BCH. Okay, so we just reduced this form. Here we have just put the value for b. B is this h by 8 pi square I c. So we just put the value of b here. So BCH, this becomes BCH j into j plus 1. J is quantum number, rotational quantum number. Now we put the value of 0 in this j, we will get is 0. Then we put 1, so we will get this 2 BCH value for this rotational energy level. Okay, so these are the rotational energy levels for all the values of j, 0, 1, 2, 3. Okay, so this is rotational spectra. Here, when we get rotational spectra, we need a transition. Okay, so here it is a rotational spectra, rotational energy levels. Now, when the molecule will absorb energy, it will go to higher energy state. Okay, so first, there is a selection rule which states that only plus or minus 1 these transitions are allowed. Okay, so the difference between two rotational quantum numbers must be plus or minus 1, plus for absorption, okay, and minus for emission. Okay, so plus 1 we can say absorption spectra and minus 1 emission spectra. So this is the selection rule. That means only adjacent energy levels or adjacent transitions between adjacent energy levels are allowed. So this we can say this is also possible, this is also possible, this is not possible. Okay, so here it is emission spectra, this is absorption spectra, this is emission spectra. Now from this diagram only we can see the difference. Here 2 BCH, here 4 BCH, difference between two energy levels of rotational spectrum. Okay, so these are the difference between two adjacent energy levels. Now here we can see if in mathematical form here the PJ level, okay, lower level, and then corresponding adjacent higher level. Now here it will change this value. First j plus 1, so j plus 1, here j plus 1. So that will be j plus 2. Now h nu will be E j plus 1 minus Pj. That means the difference between two energy levels, h nu E is equal to h nu, we know this. Okay, so that will be small amount of energy. Now here just subtract this from this, so we will get 2 BCH j plus 1. Here we can get this energy in terms of wave numbers. Okay, mu bar will be h mu by hc, we know this. So that will be 2 b, ch will get cancelled, and j plus 1. So this will be difference in terms of wave numbers. So here 2b j plus 1, we can show this difference using wave numbers also. Okay, so that will be in terms of wave number. Okay, if I erase the ch, it will be in terms of wave number. So in last point we are studying molecule can rotate, and due to this its energy levels changes. Okay, so now vibrational energy levels, you know, a molecule, a diatomic molecule can vibrate. Okay, but for vibrational molecules we need heteronuclear molecules like HCl, okay, where the dipole moment is possible, okay, to vibrate the molecule. Okay, so just consider a diatomic molecule which is vibrating, but in this case it is vibrating. We will consider its bond as a spring, massless spring. Okay, so let's consider this M1, M2. So this will be a two-body system, a two masses with one spring. Now this system, this molecule will vibrate in x-axis. So this vibration we can take it as a simple harmonic force. Now as we are considering this spring with spring constant k and these two masses, just consider a coordinate system. From this center we know it's x1, from here it is x2. So this distance will be x2 minus x1. Now this distance is x2 minus x1 is in when the system is in vibration. Okay, so it can compress, expand, compress, stretch. Okay, so that will be this distance, and this distance when the molecule is at rest we can say, so this will be L. So if we want to show a displacement, we need to subtract this one from this. Okay, so this will be the displacement x. Here x2 minus x1 is an instantaneous length of this spring or this system. Okay, the internuclear distance between them. This L is a normal. Okay, it's normal distance between these two molecules, these two atoms. Okay, so this L is a normal or atomic, we can say at room temperature when the molecule is not vibrating. So that will be the distance L, and this x2 minus x1 is nothing but a instantaneous length of this system when it is vibrating. Okay, when it will vibrate, this x2 minus x1 will be less than L. If it is compressing, it will be less. If this system is stretching, this will be a bigger value. Then this x will be a positive displacement. So we can imagine this one here. Okay, so if it goes to this, okay, here. So this is increased distance now. So this is a bigger distance as compared with L. So this will be positive displacement. We can see it is positive displacement. Okay. So if the vibration happens like this, then it will be a smaller value and the displacement will be negative. We can see here negative displacement. Okay. Here we are studying the derivation for vibrational insulators. Now we know what is the vibration of a molecule. Then we just consider two atoms as two masses M1 and M2, and the bond between them as a spring. Okay, so mass is spring and spring constant P. Now when system will vibrate, it will have a restoring force. Okay, so consider these masses have changed their mean position. So here now at these stages they will have a restoring force. Okay, so when it will go, the molecule will stretch out, it will have a restoring force. Due to this, we can formulate the equations of motion. Okay, so for spring mass system, a simple harmonic motion, we know these two equations of motions. How do we derive this? F is ma. So this A is here, we can see M is here. So force, this is equation of motion. So nothing but v square x1 by v square here. First derivative which of displacement or distance is nothing but velocity, and the second derivative is nothing but acceleration. Okay. So here ma, and this one is for k is spring constant and x is a positive displacement of first mass. Then here it is a negative displacement, hence minus x. So that will be for a second one, because here the direction is opposite of each displacement. So we are taking one displacement as a negative one. Okay, so that will be for the second one. So these are the equations of motion. Now we will solve these two equations of motion here. Okay, now for the first equation we just multiply m2 by m1 plus m2, and for the second equation we just multiply with m1 plus m1. So that will be this resultant equation. Here we just multiply with m2 and m1. Here we just rearrange these two terms. Okay, we can see here. Now if we reduce, if we solve these two, we will get m1 m2 m1 plus m2 common. Okay, so taking common outside, and here we just adding these two because the denominator is same. Now here this m1 m2 we can take this as a reduced mass mu. Okay, we know this. Now here this cancels out, and here what we did, the minus L, why we added the minus L? Because L is a constant. We know the constant distance between these two when they are at room temperature, the mean positions. So that will be constant. When we take this its derivative with respect to time, it will be 0. So if we take it or not, it doesn't matter. So we just taking it for our calculations. Now here x2 minus x1 minus L, we know this is as displacement x. So just put this value here, you will get a reduced mass and the acceleration here, then minus kx. After solving this, take this side, and here take this again on the left hand side, then right hand side will be 0. We know this equation. So what is this? This is nothing but omega naught square, which is nothing but a natural frequency of a simple harmonic oscillator. Okay, so omega naught square, omega naught is here, under root k by 0. So that will be the natural frequency of oscillation for a simple harmonic motion. So from this equation we can see it is a equation of motion for a single body. So we just reduced a two body problem into a single body problem. Okay, so this is its equation of motion for a simple harmonic oscillator. Okay, frequency, natural frequency of oscillator. Here we can reduce it into a frequency of a small oscillation mu naught. So omega naught by 2 pi, the relative frequency for small oscillations. We know we use only small oscillations, okay, in our calculations. So for the simple harmonic oscillator, we will use small oscillations frequency, natural frequency of small oscillations mu naught. Now, according to quantum mechanics, we have the energy value for, or the expression for energy of a diatomic molecule, a vibrating diatomic molecule or a oscillator. We have 3 plus half into h mu naught. Here, this mu naught is nothing but this one, okay, this natural frequency of vibration for the simple harmonic oscillator. Now, h is Planck's constant and v is a obviously vibrational constant, vibrational quantum number. So that will be a vibrational quantum number v having value same as rotational quantum number 0, 1, 2, 3, 4 and so on. So from each of these values, putting these values in this equation, we can plot all these energy levels, vibrational energy levels. So these are the vibrational energy levels. Now here, as same as rotational energy levels, we have a same selection rule for these transitions. Delta V will be plus or minus 1. Similarly, plus or minus 1. So this is absorption going to higher energy level, and this is emission going down to lower energy level. So this is plus 1, this one is minus 1. So that is a selection rule. Here we can see a difference between adjacent levels. This the transition between adjacent levels is only allowed, okay, not the from these two, okay, for example. So here we can see the difference between these two is a constant one, that is h mu naught. You see at every level we have this h mu naught same. So vibrational level, energy levels are discrete and equispaced, okay.